A small bouncy ball, or Spalding, of mass 0.25 kilograms with a momentum of 1.2 kilogram meters per second, and of course this also is Newton seconds, all right, both units work. It approaches a large door at rest. The ball bounces straight back with a momentum of 0.90 kilogram meters per second. Find the velocity of the ball before and after the collision, and then what is the kinetic energy of the ball before the collision and after the collision? Is this collision elastic? Explain your reasoning. Calculate the change in momentum of the ball, and then what is the magnitude and direction of the impulse exerted on the ball by the door and the door by the ball. So we want to find the velocity of the ball before the collision and then after the collision. So initially the ball moves to the right with an initial momentum of 1.2 kilogram meters per second. It hits the wall and rebounds with a final momentum of negative 0.90 kilogram meters per second. That's very key. Okay, so here's what we were given, right and left. We have to assign, well, we don't have to, but typically we do it. We're going to have the initial momentum is positive because it's to the right, and then the left, we'll say that's an initial negative momentum. The negative sign for that final velocity is going to be very important, and final momentum. So here's our initial momentum. V0, we're trying to find the initial velocity. So that's the initial momentum over m. Where did that come from? Here's your general equation for momentum, mv. Divide both sides by mass after you switch it around, and you find velocity is p over m. So we just defined right as positive, pretty standard. So we put in 1.2 kilogram meters per second for the momentum and divide it by 0.25 kilograms, and we get an initial velocity to the right, because it's positive, of 4.8 meters per second. Then, after the collision, which is going to be our scenario 2 here, we have a negative momentum because it's to the left. So we have a final momentum that is a negative 3.6 meters per second. So please make sure you're comfortable with this, because we're going to need that for the next part. Now, what is the kinetic energy of this ball both before and after the collision? Here, it doesn't matter what sign the velocity is. Why? Because we're squaring it, right? Because energy is always going to be positive here. So the kinetic energy at first is 2.88 joules. And then, after the collision, it's going to be less, right? Because the velocity is less. And fortunately the math checks out, 1.62 joules. The question is now, is the collision elastic? Explain your reasoning. No, I always like quick answers like that. But the kinetic energy before the collision was 2.88 joules, after it was 1.62 joules. Since the kinetic energy decreased, it is not conserved. It would have to be the same before and after for this to be an elastic collision. And that's what we're saying here. Elastic collisions conserve kinetic energy, so this collision is not elastic. What is the magnitude and direction of the impulse exerted on the ball by the door? Well, the impulse is change in momentum. So we have our P final minus P initial, and we have this up here. And remember we said earlier the signs were important? PF, that's to the left, so we need a negative sign here for the final momentum of the ball, minus the positive momentum because it's to the right, and we get a negative impulse of 2.1 kilogram meters per second. The negative sign indicates that the impulse is directed to the left. Now, I equals F delta T, so this all makes sense. The force that is exerted on the ball by the door is which way? It's to the left, right? It's pushing it back to the left. That's a negative force with our convention, so the impulse is also negative. What is the magnitude and direction of the impulse exerted on the door by the ball? Since the door exerts a force on the ball to the left, the ball exerts an equal force to the right on the door, as explained by Newton's third law. Since impulse is force delta T, the impulse exerted on the wall is the same magnitude but opposite in direction. Okay, so the impulse that is exerted on the door by the ball is a negative of the impulse exerted on the ball by the door. So we plug in the negative 2.1 kilogram meters per second there. The negative in front of it, negatives go away. And the impulse that the ball exerts on the door is in the positive direction, which makes sense. It's pushing it to the right. And it's 2.1 kilogram meters per second.